given n pairs of parentheses, generate all combinations of valid parentheses. If you are given three pairs of parentheses will generate output of length of 6. You're supposed to generate all the valid combinations. And these are all valid because when you have an open, you are always closed. And you never have situations where you have more closed than open. If you start off with a closed, you're not valid. Every time you are tasked to generate all the combinations of something, the algorithm is always backtracking. What is backtracking? Backtracking is a form of recursion. It involves building a solution incrementally, bit by bit. It involves making a choice which may or may not fail. If the choice fails to satisfy the constraint, we take back that choice or redo that choice. That's why it's called backtracking. Backtracking always involves three core concepts. The choice, in our case, since we're generating parentheses, the choice is either an open or a close. For example, if our current string looks something like this, and we are supposed to generate three pairs, our next choice may be open, may be closed. However, if our current string looks like this, our next can only be a close. If it is open, it's not valid anymore. So open will be a failed choice. In order to know if something failed or succeeded, we need to know the constraint. The constraint involves the open and close parentheses, where at any time you cannot have more close than open, meaning your open must be greater than equals to close. And at any time, your open cannot be greater than your number of parentheses. The open have to be less than equals to n. What is the goal here? The goal is to have output result that is of length n times 2. I'm going to redefine some variables. Instead of defining open as the number of open parentheses, I'm going to redefine it as the number of leftover open parentheses that we can place. Meaning, we initialize open as 3 if we're generating 3. The total number of open we can place is 3. The total number of close we can place is also 3. Anytime we place open, the leftover open we can place is 2. So if your string looks like this, because we place the open, the number of leftover opens is 2. If we place close, now close becomes 2. According to this kind of definition, open must be greater than -1. Open being negative, that means you have overplaced, meaning you have placed to more than n. The other constraint is open has to be less than equals to close in order to be valid. It may sound unintuitive because open must be smaller than equals to close to be valid because of the way we define open. Open is the leftover count. It is not a current count. So if my close is 2, meaning I decrement close by 1, this is not valid. If your open is greater than close, it's not valid anymore. So open has to be less than equals to close. Now let us code C++. We initialize the result array as result. Because we are doing a recursive function call, we are declaring a helper function. We take in the result. We pass in reference because we are going to modify it. we need two integers, open count and close count, where both are the leftover count of open parentheses and close parentheses. Let's call it both initialized to n. We also need a string to hold the current string, where in the end, if the string looks something like this, we push to the result array. Let's call it s, pass it in. I'm going to pass by reference. In JavaScript, you cannot pass string or integer by reference, but in C++ you can. By passing in reference, you are not doing any copies. So no matter what call stack you are in, you are always operating on the same string. Now let's check when will it fail. The constraint is open must be greater than -1. So when does it fail? Open less than 0, it fails. Another circumstance where it fails is when open is greater than C. Because it fails, we do nothing. Now, when do we succeed? We succeed when the length is n multiplied by 2, or in another word, open has exhausted its count, close has exhausted its count. So open exhausted from count all the way from 3 to 0, close also 0. So both are 0. Push string to the result array. Else, we are work in progress. By work in progress means we are supposed to continue adding parentheses to our current string. Now the decision is, should we add the open parentheses or should we add the close parentheses? In backtracking, the idea is to make the choice and worry about consequences later. The worry about consequence is already being coded here. So for now, let's just add left. Then we undo the choice, add left, undo the choice, aka remove the left, and add, it shouldn't be left, it should be open, then undo choice. Add open means s.pushback open. Now this is a very C++ syntax. In almost every other language, you would do something like this, but in C++ this is not desirable because s plus equals to something means you are creating a string that is s plus this and assigning that new string to s. This is a linear time complexity operation, whereas s.pushback, let's check out the documents. It is generally amortized constant, but up to linear. So this is up to linear, this is definitely linear. So this is not desirable code. It has a performance hit. Then we do recursive function call. Because we make the choice of open, our open count decrement by 1. We undo the choice, pop back just means remove the last character. Add the close parentheses, make the call, your close will decrement the count. Then pop. Let's test it out. It seems to work. Well, it does work. Now, a little tip for people who are C++ beginners. Do not do this, all right? You may see other people code like this, where they will just put something like this. I'll walk you now just to make sure it still runs. So it still runs. So what is the difference? Just now I told you we were passing string by reference. We use this sign. But now, without that sign, we are passing string by copies. String copying is extremely expensive. Although our syntax now, our code is very clean, our helper function only has 4 lines as opposed to before, we have extra 4 lines, meaning we have 8 lines. So now the syntax looks very cleaner. However, any experienced C++ programmer will tell you this is very bad code. So a better way to do it is to, by the way, this also does not work. In case you are wondering, the reason we have to separate into 3 lines is because, well, just now, let's prove to you it actually doesn't work. The error message is cannot bind non-const L-value reference. Well, this is really overkill, but the general idea is you cannot write code like this. You can only pass in S because the value of a reference variable has to be known at compile time. And this value is only known at runtime. So what you need to do is to separate into 3 lines. Modify the S, make the function call, remove that last character. So this is what you need to do. I know you are adding in more lines of code, but any experienced C++ programmer will tell you this is much better code because you're avoiding string copying. So I'm going to submit now. Okay, it does work. Now let's walk through the call stack. I'm going to walk through the code line by line so you know exactly what is going on. We're going to use the example where we are going to generate 2 pairs of parentheses. In these 2, our open and close initially both are 2 and rest is empty. Now we check if it is failing. O is not less than 0 because O is 2. O is the same as close, so it is not greater, so fail doesn't pass. It's not failing, it's a success. Neither of them are 0, so it's not success, meaning we are work in progress. Let's add an open. S.pushback left. So this shouldn't be result. It should be named as S. Our string is now has a left. We enter the call stack with the value of O minus 1. Our S is still 1 open parentheses. Is it failed? By the way, after we come back of the call stack, we will run s.popback. Bear in mind, this is what we'll run after we come back of the call stack. Okay, now into this call stack. Open 1, close 2. Is it failing? No. Is it success? No. Add an open. Our S is now like this. We are not, by the way, we are not doing any string copies. So in any call stack, in every call stack, we are always working on the same string. You can imagine it like a global variable. Then we enter another call stack. O with the value of O is 0. Close is the same. Is it failing? No. Is it success? No. Work in progress, add an open, s.pushback. S now add another one. Now with our human eyes, we know this should be failing. But our code does not know yet. It is making the decision anyway. So let us see when will our code know this S is failing. All right. So we entered another call stack with the O value -1. C is still 2. Okay, we enter the call. Yeah, we're going to the call stack. Is it failing? Yes, it is, right? Because our O is -1. -1 less than 0, so return. This call stack is returned. So you see our prevent failing mechanism is in working. When we were making the choice, we were making the choice randomly. But in the call stack, in the next call stack, it immediately detects it is failing, so we return. I hope you understand the intuition behind backtracking is we are making a choice blindly that may fail. But once we fail, we reach the backend, we return and redo that choice. How do we redo the choice? Remember, after we come back of the call stack, we execute this line, right? S.popBack. How do you pop back? You remove the last choice. So this is how we redo the choice. You messed up, so you redo the choice. That's why it's called backtracking. You hit the dead end, then you come back, redo the choice. Backtracking. Now we add a close. Our call stack will have O with 0 and C will be 1. Note after we come back to the call stack, we will execute this line. All right. So we enter the call stack. Is it failing? No. Is it success? No. And stop pushback. We are still pushing back the front. This should be failing, but the code doesn't know. We enter the call stack. O -1. Is it failing? Yes. So we pop back. After we pop back, where do we go? We go to here, pop back, push back the right, push back the close parentheses, go into the call stack with the value of C -1. Now, into new call stack, fail is a no? No. Success? Well, yes, right? Because O is 0, close is 0, it is. So our res will now have the result of this. And return. So we come back of the call stack, remove this, and back to 0, 1. I hope this gives you some intuition. I'm not going to walk through the whole thing, but I believe this is a good demonstration of what backtracking is. Backtracking is about making a choice, even it may end up wrong. But it's okay, because after the recursion, we are going to undo the choice anyway. If the choice ends up being succeeded, we push this string to the result array. I hope this exercise gives you an idea of what backtracking is and the call stack. Now let's do JavaScript. What I'm going to do is to refer back to my C++ solution. We have a res, we have a string of s, we have a res, which is array, we have s, which is string. We have a function call. Now in JavaScript, we're going to use res as a global variable. So we only put in O, C, and S. Function will be a constant. Copy paste. See, this is something nice about JavaScript and C++. You can copy paste code. If you write Python, you can't do that. You don't need to do that, so let's copy paste this one. No need for res. S plus open. s plus back. Call it. See how it goes. Submit. There we go.